You can learn to drive a car by getting the keys, having someone show you how the steering wheel, the gas, and the brakes work. Try it out in a quiet parking lot and then ease yourself onto the open road. And before long, you're able to get yourself to the grocery store and to a friend's house, and you can get done the basics. Now, contrast that with becoming a race car driver. In that case, you want to be able to get as much performance as possible out of your car. And to do that, you need to know how it works down to the nuts and bolts. That's the process of looking under the hood or opening the black box. If you want to get the most out of your tools, then how things work really matters. So to show you what I mean by this, for most of us, beginning machine learning or software engineers, this is what a support vector machine looks like. Here is the black box. You import scikit-learn, queue up a simple example and run it, and you're done. Here are the keys, here's the steering wheel, go. But to get the most out of it, you have to go deeper. My goal in this talk is to walk you through the process of going deeper, but more importantly, to show how any of us can go deep on any subject that we want to that we want to master. So as I tackled support vector machines, which were fairly new to me when I started this presentation, the first step I took was to read the scikit-learn documentation. This is what I came across. It's not particularly helpful to me being new to support vector machines. It's a nice, concise summary of the basic principles of how they work, but it doesn't explain it to someone who doesn't already know them well. One thing that the scikit-learn documents did provide was this great diagram showing here 2 different colors of points being separated by a line. That line looks kind of like a road where those 2 lanes are as wide as they can possibly get before they start touching data points. This was helpful. My next step was to go find a nice tutorial and read it. I found one that was highly recommended and started reading through it. And I saw definitions and tables and equations and graphs and diagrams and plots, and very soon got very overwhelmed, and there were theorems, for God's sake. And I felt strongly that it was probably important stuff, but it was not very accessible to someone who is new to the topic. So I took a step back, I set that aside, and I went to YouTube. And I pulled up some of the most popular videos on support vector machines, and in the course of doing this, saw multiple explanations of what they are, what they're used for, how to visualize them, how the math underneath them works. And the principles finally started to click. They began becoming clear in my brain. Following this, I went and found some more blog posts, again from a variety of posters, each with their own way of visualizing how they work, of explaining the principles behind it, and now the equations and the math and the definitions started to make a little sense. Enough so that I, in the next step, started to try to explain it to myself. And the way I do this is by drawing pictures. And so I started illustrating some of these concepts in a way that would make sense to me in my brain. Now that the ideas underneath support vector machines, at this stage, they're crystals, they're nuggets, but they're scaffold, but they're not fleshed out. So to do this, I find it very helpful to choose a toy example. This is a bit of an art, it's trial and error, but finding an example that's simple enough that you understand it completely and you know exactly how it should work, but it's just complicated enough to illustrate the principle. So for this one, I settled on fruit. So imagine that we have fruit. It can either be small or large or yellow or purple. Now, any small fruit is a plum. If it's yellow, it's not yet ripe, but if it's purple, it's ripe and good to eat. Any large fruit is a peach. If it's yellow, it's great to eat, but if it's purple, it's rotten. You don't want to eat it. So in this example, we have in the world of peaches, there's a size axis and a color axis. And you can see the good things to eat are at the upper left and the lower right. Now, in this example, once you have this example, if you can get it to where you can explain it to, roughly like a 12-year-old, a sixth grader, which means that you use words and ideas that are common, no jargon, or if you do use a jargon term, you explain it thoroughly. So here's my attempt to do that for support vector machines. So imagine you have peaches, and they can be any color between yellow and purple, and you would like to figure out which ones are good to eat. You'd like to know, in fact, if you get a new peach based on its color, whether you should eat it or not. So what you do is you get a bunch of peaches and you grab one and you try it. You get one that happens to be yellow, you taste it, it's good. So you make a green circle and put it at the point that represents its color. You grab another one that's pretty purple and you taste it and it's nasty, it's rotten. So you put a black X at the point that represents its color. And you do this again for a few more peaches, some yellow ones, some purple ones, some ones in between. And before long, you have a data set that looks like this. The green circles all show good peaches, the black X's show bad peaches. Now that you have all this data, you would like to make a prediction. Based on a peach's color, do you expect it to be good to eat? Support vector machines allow you to do this. And what they do when you have two groups of data is they come and they put what looks like a road in between them. There's a dotted center line and then two lanes, and it tries to make that road as wide as it can possibly get until the outside of those two lanes bump up against your two data sets. The center line is the divider between the two groups. Anything to the left of that will be assumed to be good to eat. Anything to the right of that will be assumed to be bad to eat. And the lanes on either side are called margins, for lack of a better term. Now, imagine though that in this set of peaches, this can be trickier. What if you have some that don't really fall with the group? You get some yellow peaches that just don't taste right, or you get a purple peach that for some reason tastes amazing. Now the data set, there's nowhere you can draw a line that separates the green circles from the black X's. But what you can do is still create a dividing line with its margins, but any data point that is on the wrong side of its margin gets a penalty based on how far it is over. And so you can move the position of this dividing line and the width of its margins to take that penalty and add that penalty in and still make that as small as you possibly can. So you can still use support vector machines in cases where your data isn't completely separate. The fancy term for that is linearly separable. Just means you can't separate it with a line. So it can handle non-linearly separable data. Now let's look at a different case. Instead of just peaches, we have peaches and plums. The good ones, we either want to eat yellow peaches or purple plums. A yellow plum isn't ripe and a purple peach is rotten. So we can do the same thing in this world. We try a bunch of fruit of different sizes and different colors. We find that the yellow peaches are delicious. We find that the purple plums are delicious, but the yellow plums are terrible and the black peaches, the purple peaches are terrible. So we end up with a data set that looks like this. The challenge now is that if we try to draw a line to separate these out, it's not just that a few data points are going to be a little bit off. There's a whole chunk of our data that we're missing. We're not capturing it well. So this data is obviously not linearly separable. To help us visualize this, I went and took it into Python and made a different visualization of it. But it's the same thing, green circles and black X's. We'd like to try to separate them. And in this case, we can't with a line. Now, support vector machines have an answer to this. What you do is you imagine that all of these data points are not on a flat plane, but they're on a sheet of rubber. And you can pick that sheet of rubber up and you can stretch it and bend it and warp it however you want. And you can probably visualize here that if you take that and bend it just right and slice it, you can separate out the good to eat fruit from the bad to eat fruit. And this is exactly how you would do it. If you can now, with a single straight slice, you can separate these things out nicely. This trick of bending your sheet of paper, of warping it, is called the kernel trick. And it refers to how it's calculated. But in practice, all you need to know is you can take this space that your data is in, this paper that it's on, and twist it and bend it however you want. You can take and hold down the middle and pull up all four edges. Or you can pull up all four edges and pull up the middle and leave a little ring low around the middle, or low around the center. Or you can take it and pull it up and pull it down and make it like an egg crate so that you can capture really irregularly spaced data, and with a single slice, you can separate it all out from each other. So the kernel trick is really powerful. And in fact, there is no limit to what you can do with this space to bend it. To illustrate another way that it's powerful, let's consider a slightly different problem. Now we have fruit. We don't care about the size, but we have 5 different colors. Green peaches are unripe. They're not yet ripe. Yellow peaches are ripe, so they're good. Orange fruit is an unripe plum, and a purple is a ripe plum, and then a black fruit is rotten. So the good ones to eat are the yellow peaches and the purple plums. Any other color is bad to eat. Now you can see that all of this data is just on one line, but there's no nice way to slice it to separate the green circles from the black X's. Now we can use the kernel trick. We can take that line essentially and bend it however we want. One way to do that is to just make a single bend in it, like a smiley face. And you can see that, great, we bent it, but still those circles and X's are not laid out so that with a single cut, we can separate them from each other. Now, the cool part about the support vector machine kernel trick is that you can come back and bend your space again in a different direction. So this represents a 2-dimensional kernel. And now it's not too hard to see that with the right slice, you can come in there with the plane and separate out those green circles from those black X's. Now, if you look carefully, you'll notice that this slice is actually not exactly the one you'd want. It kind of misses, but you can imagine where it would go to separate those out. So here we did 2 different warpings. We took our line and we bent it one direction, and then we bent it another direction. Because of the math, it's a little bit mind-blowing, but you can actually take whatever space your data is in, and you can bend it in an infinite number of directions to make it so that you can slice it and separate out your 2 groups of data. So that is pretty powerful stuff. This is what support vector machines do. They take and find the best slice that separates out 2 groups of data, and if your data is hard to separate, you can warp and twist your space until you find a way to separate it. Okay, so that's the explanation. Now comes the most important part. In addition to understanding the strengths of a method, you have to understand its weaknesses if you're going to use it well and push it to its limits. So, with support vector machines, issues include if you have data with lots of error. So if you notice, any time that we're finding a slice between 2 groups of data, the location of that slice depends almost entirely on the very nearest data points. The other ones, it doesn't matter if they're close to the margin or miles away from the margin. It's those nearest data points that determine exactly where that margin is going to be. And if each of those has a lot of error associated with it, then that error gets a really loud vote, more so than most of your data. So that is an issue. Another way that it can break is if you choose the wrong kernel. If you look back at the original data set where we were bending our paper like a sheet of rubber, if we bent it the wrong way, we would not be able to separate out our data sets. We had to bend it just the right way. That's choosing the right kernel. And the act of choosing the right kernel is an art, and it's done by trial and error and, after a while, by experience. And then finally, large data sets can break support vector machines. Calculating the kernel, some kernels especially, can be very expensive, take a lot of computing power. And so if you're not dealing with just hundreds of data points, but billions, then the amount of time to calculate those is prohibitive. So with large data sets, you have to stick with linearly separable problems. So you have to go back and hand engineer features that help your data get separated out. Help it so you can separate it with a straight line, single cut. So each of these requires a human in the loop to determine when it's a problem and to work around it. This is important to know. This means that support vector machines are powerful, but to get the most out of them, you need someone who has used them quite a bit and understands them well. This doesn't mean that they can't be used, but this is important to know when you're deciding what method to use on your problem. Now, taking a step back, that was a quick walk through support vector machines. Hopefully you understand it now a little bit better than you did before if you were new to it. And now going into another project, you know what you need to do to make good use of it. A comment on the process. We went through this together. There was no formal education, no coursework, no textbook, no professor, no permission granted, no special libraries, nothing purchased. This is all information that's out there. This is something that you can do with any tool you want. You can take and open the box and see what's inside. You can lift up the hood and you can see what the pieces are and how they work together. It's not an easy process, and sometimes it's quite painful, but it is something that you have at your disposal. And it's something that, in the cases of my key tools, I have found it very worth my while. So I encourage you, when you have something that you think you might need to use heavily, take some time, open the box, figure out how it works so you go from a grocery getter to a really high-performing race car. Thank you.
Hello, welcome to How Convolutional Neural Networks Work. Convolutional neural networks, or ConvNets or CNNs, can do some pretty cool things. If you feed them a bunch of pictures of faces, for instance, they'll learn some basic things like edges and dots, bright spots, dark spots. And then because they're a multi-layer neural network, that's what gets learned in the first layer. The second layer are things that are recognizable as eyes, noses, mouths. And the third layer are things that look like faces. Similarly, if you feed it a bunch of images of cars, down at the lowest layer, you'll get things, again, that look like edges. And then higher up, you get things that look like tires and wheel wells and hoods. And at a level above that, things that are clearly identifiable as cars. CNNs can even learn to play video games by forming patterns of the pixels as they appear on the screen and learning what is the best action to take when it sees a certain pattern. A CNN can learn to play video games, in some cases, far better than a human ever could. Not only that, if you take a couple of CNNs and have them set to watching YouTube videos, one can learn objects by, again, picking out patterns, and the other one can learn types of grasps. This then, coupled with some other execution software, can let a robot learn to cook just by watching YouTube. So there's no doubt CNNs are powerful. Usually when we talk about them, we do so in the same way we might talk about magic. But they're not magic. What they do is based on some pretty basic ideas applied in a clever way. So to illustrate these, we'll talk about a very simple toy convolutional neural network. What this one does is takes in an image a two-dimensional array of pixels. You can think of it as a checkerboard, and each square on the checkerboard is either light or dark. And then by looking at that, the CNN decides whether it's a picture of an X or of an O. So for instance, on top there, we see an image with an X drawn in white pixels on a black background. And we would like to identify this as an X. And the O, we would like to identify as an O. So how a CNN does this has several steps in it. What makes it tricky is that the X is not exactly the same every time. The X or the O can be shifted, it can be bigger or smaller, it can be rotated a little bit, thicker or thinner, and in every case we would still like to identify whether it's an X or an O. Now the reason that this is challenging is because for us, deciding whether these two things are similar is straightforward. We don't even have to think about it. For a computer, it's very hard. What a computer sees is this checkerboard, this two-dimensional array, as a bunch of numbers, ones and minus ones. A 1 is a bright pixel, a minus 1 is a black pixel, and what it can do is go through pixel by pixel and compare whether they match or not. So to a computer, it looks like there are a lot of pixels that match, but some that don't, quite a few that don't actually. And so it might look at this and say, I'm really not sure whether these are the same. And so it would, because a computer is so literal, it would say, uncertain. I can't say that they're equal. Now, one of the tricks that convolutional neural networks use is to match parts of the image rather than the whole thing. So if you break it down into its smaller parts or features, then it becomes much more clear whether these two things are similar. So examples of these little features are little mini images. In this case, just 3 pixels by 3 pixels. The one on the left is a diagonal line slanting downward from left to right. The one on the right is also a diagonal line slanting in the other direction. And the one in the middle is a little X. These are little pieces of the bigger image. And you can see as we go through, if you choose the right feature and put it in the right place, it matches the image exactly. So, okay, we have the bits and pieces. Now, to take a step deeper, the math behind matching these is called filtering. And the way this is done is a feature is lined up with the little patch of the image, and then one by one, the pixels are compared. They're multiplied by each other, and then added up and divided by the total number of pixels. So to step through this, to see why it makes sense to do this, you can see starting in the upper left-hand pixel in both the feature and the image patch, multiplying a 1 by a 1 gives you a 1. And we can keep track of that by putting that in the position of the pixel that we're comparing. We step to the next one, minus 1 times minus 1 is also a 1. And we continue to step through pixel by pixel, multiplying them all by each other, and because they're always the same, the answer is always 1. When we're done, we take all these 1s and add them up and divide by 9, and the answer is 1. So now we want to keep track of where that feature was in the image, and we put a 1 there. Say, when we put the feature here, we get a match of 1. That is filtering. Now we can take that same feature and move it to another position and perform the filtering again. And we start with the same pattern. The first pixel matches, the second pixel matches. The third pixel does not match. Minus 1 times 1 equals minus 1. So we record that in our results. And we go through and do that through the rest of the image patch. And when we're done, we notice we have 2 minus 1s this time. So we add up all the pixels, which add up to 5, divide by 9, and we get a 0.55. So this is very different than our 1. And we can record the 0.55 in that position where we were, where it occurred. So by moving our filter around to different places in the image, we actually find different values for how well that filter matches or how well that feature is represented at that position. So this becomes a map of where the feature occurs. By moving it around to every possible position, we do convolution. That's just the repeated application of this feature, this filter, over and over again. And what we get is a nice map across the whole image of where this feature occurs. And if we look at it, it makes sense. This feature is a diagonal line slanting downward, left to right, which matches the downward, left to right diagonal of the x. So if we look at our filtered image, we see that all of the high numbers, 1s and 0.77s, are all right along that diagonal. That suggests that that feature matches along that diagonal much better than it does elsewhere in the image. To use a shorthand notation here, we'll do a little X with a circle in it to represent convolution, the act of trying every possible match. And we repeat that with other features. We can repeat that with our X filter in the middle and with our upward slanting diagonal line in the bottom. And in each case, the map that we get of where that feature occurs is consistent with what we would expect based on what we know about the X and about where our features match. This act of convolving an image with a bunch of filters, a bunch of features, and creating a stack of filtered images is we'll call a convolution layer. A layer because it's an operation that we can stack with others, as we'll show in a minute. In convolution, one image becomes a stack of filtered images. We get as many filtered images out as we have filters. So convolution layer is one trick that we have. The next big trick that we have is called pooling. This is how we shrink the image stack. And this is pretty straightforward. We start with the window size, usually 2 by 2 pixels or 3 by 3 pixels, and a stride, usually 2 pixels. Just in practice, these work best. And then we take that window and walk it in strides across each of the filtered images. From each window, we take the maximum value. So to illustrate this, we start with our first filtered image. We have our 2 pixel by 2 pixel window. Within that pixel, the maximum value is 1. So we track that and then move to our stride of 2 pixels. We move 2 pixels to the right and repeat. Out of that window, the maximum value is 0.33, etc., 0.55. And when we get to the end, we have to be creative. We don't have all the pixels representative, so we take the max of what's there. And we continue doing this across the whole image. And when we're done, what we end up with is a similar pattern, but smaller. We can still see our high values are all on the diagonal, but instead of 7 by 7 pixels in our filtered image, we have a 4 by 4 pixel image. So it's half as big as it was about. This makes a lot of sense to do if you can imagine if instead of starting with a 9 by 9 pixel image, we had started with a 9,000 by 9,000 pixel image. Shrinking it is convenient for working with it. Makes it smaller. The other thing it does is pooling doesn't care where in that window that maximum value occurs. So that makes it a little less sensitive to position. And the way this plays out is that if you're looking for a particular feature in an image, it can be a little to the left, a little to the right, maybe a little rotated, and it'll still get picked up. So we do max pooling with all of our stack of filtered images and get, in every case, smaller set of filtered images. Now, that's our second trick. Third trick, normalization. This is just a step to keep the math from blowing up and keep it from going to 0. All you do here is everywhere in your image that there is a negative value, change it to 0. So for instance, if we're looking back at our filtered image, we have these what are called rectified linear units. That's the little computational unit that does this. But all it does is steps through everywhere there's a negative value, change it to 0. Another negative value, change it to 0. And by the time you're done, you have a very similar looking image, except there's no negative values. They're just zeros. And we do this with all of our images, and this becomes another type of layer. So in a rectified linear unit layer, a stack of images becomes a stack of images with no negative values. Now, what's really fun, the magic starts to happen here when we take these layers, convolution layers, rectified linear unit layers, and pooling layers, and we stack them up so that the output of one becomes the input of the next. You'll notice that what goes into each of these and what comes out of these looks like an array of pixels, or an array of pixels. And because of that, we can stack them nicely. We can use the output of one for the input of the next. And by stacking them, we get these operations building on top of each other. What's more, we can repeat the stacks. We can do deep stacking. You can imagine making a sandwich that is not just one patty and one slice of cheese and one lettuce and one tomato, but a whole bunch of layers, double, triple, quadruple deckers, as many times as you want. Each time, the image gets more filtered as it goes through convolution layers, and it gets smaller as it goes through pooling layers. Now, the final layer in our toolbox is called a fully connected layer. Here, every value gets a vote on what the answer is going to be. So we take our now much filtered and much reduced in size stack of images. We break them out, we just rearrange and put them into a single list because it's easier to visualize that way. And then each of those connects to one of our answers that we're going to vote for. When we feed this an X, there will be certain values here that tend to be high. They tend to predict very strongly that this is going to be an X. They get a lot of vote for the X outcome. Similarly, when we feed in a picture of an O to our convolutional neural network, there are certain values here at the end that tend to be very high and tend to predict strongly when we're going to have an O at the end. So they get a lot of weight, a strong vote for the O category. Now when we get a new input and we don't know what it is and we want to decide, the way this works is the input goes through all of our convolutional, our rectified linear unit, our pooling layers, and comes out to the end here. We get a series of votes, and then based on the weights that each value gets to vote with, we get a nice average vote at the end. In this case, this particular set of inputs votes for an X with a strength of 0.92 and an O with a strength of 0.51. So here, definitely X is the winner, and so the neural network would categorize this input as an X. So in a fully connected layer, a list of feature values becomes a list of votes. Now, again, what's cool here is that a list of votes looks a whole lot like a list of feature values. So you can use the output of one for the input of the next. And so you can have intermediate categories that aren't your final votes, or sometimes these are called hidden units in a neural network. And you can stack as many of these together as you want also. But in the end, they all end up voting for an X or an O, and whoever gets the most votes wins. So if we put this all together, then a two-dimensional array of pixels in results in a set of votes for a category out at the far end. So there are some things that we have glossed over here. You might be asking yourself where all of the magic numbers come from. Things that I pulled out of thin air include the features in the convolutional layers, those convenient 3 pixel by 3 pixel diagonal lines at the X. Also, The voting weights in the fully connected layers. I really waved my hands about how those are obtained. In all these cases, the answer is the same. There is a trick called backpropagation. All of these are learned. You don't have to know them. You don't have to guess them. The deep neural network does this on its own. So the underlying principle behind backpropagation is that the error in the final answer is used to determine how much the network adjusts and changes. So in this case, if we knew we were putting in an X, and we got a 0.92 vote for an X, and that would be an error of 0.08, and we got a 0.51 vote for an O, we know that that would be an error of 0.49, actually an error of 0.51 because it should be 0. Then if we add all that up, we get an error of what should be 0.59. So what happens with this error signal is it helps drive a process called gradient descent. If there is another bit of something that is pretty special sauce to deep neural networks, it is the ability to do gradient descent. So for each of these magic numbers, each of the feature pixels, each voting weight, they're adjusted up and down by a very small amount to see how the error changes. The amount that they're adjusted is determined by how big the error is. Large error, they're adjusted a lot. Small error, just a tiny bit. No error, they're not adjusted at all. You have the right answer, stop messing with it. As they're adjusted, you can think of that as sliding a ball slightly to the left and slightly to the right on a hill. You want to find the direction where it goes downhill. You want to go down that slope, down that gradient to find the very bottom, because the bottom is where you have the very least error. That's your happy place. So after sliding it to the left and to the right, you find the downhill direction and you leave it there. Doing that many times over lots of iterations, lots of steps, helps all of these values across all the features and all of the weights settle in to what's called a minimum. And at that point, the network is performing as well as it possibly can. If it adjusts any of those a little bit, its error will go up. Now, there are some things called hyperparameters, and these are knobs that the designer gets to turn, decisions the designer gets to make. These are not learned automatically. In convolution, figuring out how many features should be used, how big those features should be, how many pixels on a side. In the pooling layers, choosing the window size and the window stride. And in fully connected layers, choosing the number of hidden neurons, intermediate neurons. All of these things are decisions that the designer gets to make. Right now, there are some common practices that tend to work better than others, but there is no principled way. There's no hard and fast rules for the right way to do this. And in fact, a lot of the advances in convolutional neural networks are in getting combinations of these that work really well. Now, in addition to this, there are other decisions the designer gets to make, like how many of each type of layer and in what order. And for those that really like to go off the rails, can we design new types of layers entirely and slip them in there and get new fun behaviors? These are all things that people are playing with to try to eke out more performance and address stickier problems with CNNs. Now, what's really cool about these, we've been talking about images, but you can use any two-dimensional, or even for that matter, 3- or 4-dimensional data. But what's important is that in your data, things closer together are more closely related than things far away. What I mean by that is, if you look at an image, 2 rows of pixels or 2 columns of pixels are right next to each other, they're more closely related than rows or columns that are far away. Now what you can do is you can take something like sound And you can chop it up into little time steps. And for each piece of time, the time step right before it and right after is more closely related than time steps that are far away. And the order matters. You can also chop it up into different frequency bands. Bass, mid-range, treble. You can slice it a whole lot more finely than that. And again, those frequency bands are the ones closer together, are more closely related, and you can't rearrange them. The order matters. Once you do this with sound, it looks like a picture. It looks like an image, and you can use convolutional neural networks with them. You can do something similar with text, where the position in the sentence becomes the column, and the row is words in a dictionary. In this case, it's hard to argue whether order matters. That order matters. It's hard to argue that words in a dictionary are that some are more closely related than others in all cases. And so the trick here is to take a window that spans the entire column, top to bottom, and then slide it left to right. That way it captures all of the words, but it only captures a few positions in the sentence at